So today I'll be talking about the wonderful world of prefix sums. And I'm sure you probably know it. There's a lot of, it's pretty much pre-DP, baby DP. But the idea is like this, right? Let's say you have an array of 4 numbers, right? And you want to compute the sum of, let's say, these numbers, okay? Now, normally, you would have to do a for loop and go through each and every single one. And that for loop would take about O of n time, okay? N being the size of the array you're looking through, or the subarray you're looking through, okay? So with prefix sums, it has one simple goal, and it's called a range query. Query meaning like question. Okay. Range query. It takes, and pre-computation will take O of n time. Pre-computation means you're gonna like pre-compute all the values so that you get what you want. And that takes O of n time. So what we do is, in the original array, which looked like this, we're going to pre-compute it such that we're going to take the current running sum. The idea is 3 is the sum of everything behind it, 1 and 2. 6 is the sum of everything behind it, 1, 2, and 3. 10 is the sum of everything behind it. And that's what we're going to do for prefix sums, okay? And we're going to take the sum of everything behind it. Now, this is prefix sums for addition. And I'll tell you some more interesting things later. But yes, this is what prefix sums looks like. Now the cool thing is that there's this cool function that we could do to get subarrays, or the sum of subarrays. And it goes like this. P will be the array. And it goes like J minus P minus 1. And J, sum of array from J, or I to J. And how this works is it gets all the values up until J, which is 10, and then subtracts behind everything that's outside of it, which would be index 0 in this case, right? Captures everything here, and then everything behind it, all the pre-computed prefix summed, or like the running total, is going to be deleted away. Okay, and you can see like the math behind it, right? If we take, let's instead take the prefix sum, or let's take the prefix sum of 2 and 3, right? And we're going to delete everything to the left of it, and we're also going to delete everything to the right of it. Now, our running total goes in the rightward direction, meaning this prefix sum value at this index right here is the sum of everything to the left of it, right? That's like the definition of that index, right? So automatically, it deletes everything to the right of it, the sums to the right of it. But by deleting this I minus 1 portion, it deletes everything to the left of it. It removes everything. That's the basic idea of prefix sums. And this pre-computation is only just 2 array accesses, meaning it is only O of 1 time, which is really useful. Okay, instead of doing that O of n slow for loop, which let's say we have an array of size like 1 million, right? If we wanted to go through every single element, it would take 1 million operations. In this case, it only takes O of 1, which is depending on the compiler, which means it's constant. Now, again, here's a disclaimer. If I just need to grab like the sum of numbers one time. There is no need for prefix sums. Because if it's one time, remember I said that the pre-computation it takes originally O of n time, right? Setting up that prefix sums array takes O of n time, and it would look something like this, right? It would be, I'll actually probably code it out in my code blocks, but it would probably be like int pref equals new int 5, something like that, int I is less than 5, I plus plus. Actually, what we want to do is this. What you'll usually do, what most people do for prefix sums, is they'll have an extra index, +1 index. And you'll notice that when you do the prefix sum like formula, it's j minus p I minus 1. This I minus 1 has an opportunity to go out of bounds. So what they do is they add an extra index for 0. And even though the prefix sum will look like this, theoretically, 1, 3, 6, 10, they're going to add another extra 0 at the end. Okay, and you'll see what's going on here. I'm going to start at 1, and originally the array will initialize 0 as every element. So basically this makes index 1, 0. Right. And what we're going to do is we're going to do pref I equals to pref I minus 1 plus AI. AI being the array. Okay. And actually, we can probably just do like something like this. Something like that. I think that compiles. Does it compile? I don't think so. Oh, crap. Okay, Coblocks doesn't run Java just yet. Okay, I need to set that up. But, yeah. So, again, this is what it would look like. This would still take O of n time. My point is it would still take O of n time. Okay? However, if you're doing like 1,000 operations, prefix sums can be pretty useful. If you had to do 1,000 times, it would take O of 1,000 n, right? You're going to do 1,000 for loops. And instead, if you use prefix sums, 1,000 would only take 1,000 times 1, right? O of 1 is for every query, and you're going to add n because that's like a separate pre-computation. Okay. So disclaimer, only use it when you're being queried a lot. Again, in problems like maybe you'll need like a really quick range query. That's when you'll probably need it. I spelled query wrong. Another thing that's pretty interesting about prefix sums is that it's not just addition. Anything that's reversible works. Remember, the reverse operation of plus is minus, right? And that's why we had to do that pj minus pi, right? We're taking out that left side. So one thing that also works is XOR, which looks like this caret. You'll also see it as this like kind of plus sign. And the opposite of XOR is actually just XOR, which is really weird. But if you do some like digging, you'll see it. And so in a prefix XOR, right, you can do some reversing of that. Another quick thing is you can also do some rectangle prefix sums. And you can get like a 2D matrix. And compute this in O of 1 time. Of course, pre-computation is O of n times m, being the number of rows and the number of columns, right? But still, it's pretty quick, right? Okay. And then finally, to answer the question, what can I apply this to? Here's what it will look like, right? Here's a quick problem. So imagine this, right? This is called equilibrium. This is like one of the most basic prefix sums problems. It goes like this, right? basically, you're given an array, and you want to find a point in the array. It doesn't matter what value it is. It doesn't matter what value. But that everything to the left of it must equal everything to the right of it. That's the idea. Okay. And you could think like, oh, you can pause the video and see like, oh, how can I do this? But it's not hard at all. What you'll have to do is you can take the prefix sum of this area, and then if it's equal to the prefix sum of this area, you're fine. Those are two range queries. And what would normally take O of n time, like this would take O of n time, this would take O of n time, making it O of 2n time, and then you're gonna have to like check every placement. Like, yeah, you'll have to check every single placement to see if it's a possible equilibrium point, which would also be another O of n time, and it would result in 2 of n squared, which is a little annoying. But instead, we can make this only O of 1, or O of 1 times 2 times n, making it only O of n time. I know I went a little quick, but I'll kind of review it. Basically, the solution is you go through every point as a possible equilibrium point, and then compute the left range query and compute the right range query with prefix sums. That's it. And the two would be O of 1, O of 1. Crap. O of 1 times 2. And then you would also have to multiply by n for checking each equilibrium point. And it would simplify to O of n. Okay. And the prefix sums for here would be pj minus pi minus 1. J being the equilibrium point. Actually, let's just put an e. E. Actually, no, it would just be pe because the beginning I would be 0. You're getting everything to the left of it. PE, check whether it's equal to PN minus PE. Something like that. Actually, it would probably be E minus 1 because we're not going to include E. But if you want to see it in code, I'll just quickly code it out. Okay, yeah, this is computation. I'm just going to use it. E is less than n being the size of the array. Left, actually, int left equals to brief e minus 1. Actually, yeah, we're going to do 1 because remember the first one is just like a filler. The first position in pref is a filler 0. This is the left, and then the right would be a solid n minus brief e. Yes. If left equals to right, return, sure, something like that. That's what it would look like. Yeah. That's all I have for prefix sums. I could do another problem. Look for one, like a maybe tougher problem that we can work out. But yeah, this is basically prefix sums in a nutshell.